All right, today's topic is all about graphs of exponential and log equations. But before we talk about the graphs of them, we want to talk about how the transformation works or how they translate. So with the first 5 problems that we do, we're going to see if they represent growth or decay and describe the translation. And then the next 5 problems, we just describe that translation. Okay, so the first thing that we're going to do is fill in for these little hints that we have. Hopefully you remember these from the first day, first unit. Anything that is with X is going to move the graph how? Left or right? What kind of numbers make it move to the left when we do what? Or what operation? The minus goes with the right and the positive goes with the left. It's opposite of what you think when it's with X. So anything with Y or anything at the end of the function is going to make it move up or down. What kind of number makes it move up? And down is good. So if it's at the end, and I usually say with Y, but at the end of the function makes it move up and down. If there's a negative right after the y equals, so if it's y equals a negative, it makes it reflect over the x-axis. And those are the main ones that we talked about when we did our absolute value graphs, and we did some stuff in math too. So we are going to use those things and talk about it with our first 5 problems here. So number 1 says y equals 2 parentheses 0.5 to the x plus 3. Now notice all of these things that I mentioned up here, we really just look at what's added, subtracted, and if there's a negative at the beginning. So I see this plus 3 at the end, which is going to make it move up 3. Because it is at the end. So it's not with the x. It's not in the exponent with x. Then the next thing we want to do for these first 5 problems is talk about whether this is a growth or a decay function. Is this a growth or a decay? It's a decay. How do you know? Good. We look at b. b is less than 1, so it is a decay problem. All right, let's look at problem 2. Y equals e to the x minus 4. Well, that minus 4 is in the exponent with x, so a minus 4 would make it move right 4. Now we look at b. Is b more than 1 or less than 1? What is b? It's not 0. B is the base. What is the base of the exponent? E. What is E about? Does anybody remember? It's about 2.7, which is more than 1, so it is a growth. So look for that value of B. B is the base of the exponent, and that will tell you whether it's a growth or a decay. All right, let's look at problem 3. Y equals 5 to the x plus 3 minus 1. And which way 3? Left 3, down 1. Good. We look at what is with x and what is happening at the end. So this is left 3, this is down 1. Now we pay attention to b, and b tells us we have a growth. Now, the next one actually has a little trick to it. So, we want to look at what is going on with our function here. So, y equals e to the negative x. When you put a negative with x, it does something different. A negative with x reflects our graph over the y-axis. So, when we have a negative at the beginning, it reflects over x. When we have a negative with x, it reflects over the y. Now think about what's going to happen if we reflect that graph. If you reflect it, it's going to change some things. What is it going to change? Well, let's actually graph it and look at it. So go to y equals. Y'all grab out your calculators. And it's e to the negative x. Now, go ahead and hit graph, or you might have to hit zoom 6 and look at that graph. Now, we just said on our previous problem that we had a base of e, and we said in number 2 that that was a growth. Does this graph show a growth? It shows a decay. Now, why does it show a decay? Because it was reflected. It was flipped. So when you have a reflection, it's going to flip this from a growth to a decay. Okay, so you might want to make yourself a note of that. Make yourself a little star, write a little extra note. When it reflects or when it flips, it also flips the growth and decay. All right, let's do our last one in this column. Y equals negative 2, parentheses 0.5 to the x. So we don't have anything added or subtracted, so there's no moving left, right, up, down, but it does start as a negative, which means it reflects over which axis? The x-axis. If you reflect over the x-axis, it's also going to change your growth decay. So originally, this one is a decay because of the 0.5, just like in number 1, but now it's going to change to a growth. Does that make sense? Okay. Now, when in doubt, you can always graph it, just like we did the other one. Just graph it in y equals and see if it increases or decreases, because it's going to do one or the other. So increase would be a growth, a decrease would be a decay. Just read it left or right. All right, these next few, 6 through 10, we don't put growth or decay, but we do everything else because we don't say it's a logarithmic growth, because these are all logs and natural logs. So what would you say for this first one? How does this translate? It goes left 2 because it's with the x, so left 2. And that's all that you need to say. All right, what about 7? Down 4. Yep, because it is outside of the parentheses, so it's at the end. All right, what about question 8? Good, right 4, up 1. Right 4, up 1. Question 9. There's no add subtract, but it reflects how? Over the x, because that negative is at the beginning after the y equals. And our last one. Good. Right 1, down 3. Does that make sense on how to describe the translations? Okay, great. So next what we're going to do is we're going to review graphing exponentials and also finding our key features. Yeah, the A through I stuff. So write down the equation. Go ahead and write down what A through I is. And then if you want to write it on graph paper, you can, because we're going to be graphing these. Whew. That's a good question. Thank you for changing that phrase for me. that question. No, I agree with you. No, I do miss the curriculum that was like Algebra 1, Geometry, Algebra 2, instead of like the spiral kind of learn that we do now. I felt like skills were mastered a little bit better when we did that. Well, they do. Yeah. Yeah. But yeah, like the basic concepts for like math 3 are knowing your key features and translations for all types of functions. So that's why we do so much of that. And then solving any polynomials, which we're going to do in Unit 5. And then piecewise functions, knowing some basics about that. So they give us like topics, and then they give us, it's kind of like a rule. They give us like a goals, and I hit most of them. Yeah. Yeah. History doesn't have any more state tests. They have a little bit more lenience on their topics. Kind of is. Math, no fun and games. All right, let's review how to graph this one. Now, remember when we graphed, there were 3 things that we picked out. One thing that we picked out was the A. What does A stand for in this problem? 2. And B was, or is? 0.8, yep. And the third thing that we found was HA. Now remember, HA is y equals a number. What's that number? What did you say? Not 1, but 0. Yep, that's it. Because HA is typically what's added at the end. So it's y equals AB to the x is the general formula. So A is the number in front, B is being raised to the power, and then whatever's at the end tells us our HA. So a review on how to graph this is at HA at y equals 0, we put a dotted line. Well, in this case, that would be our x-axis. Remember, HA stands for that horizontal asymptote that the graph does not touch or cross, okay? Now, the next thing that we plot from there is our y-intercept. So our y-intercept is the A value, or how far A is above this dotted line. So we're actually going to have a y-intercept at 2. And then B tells us it's a decay problem. Yep, it tells us growth or decay, and this one's going to say decay. So we start up high, we go through that y-intercept, and then it levels off. Now we can find our 9 key features. So the first one is the x-intercept. Well, does this graph touch the x-axis? No, it levels off there, it doesn't touch it, so x-intercept is none. You can also find your x-intercept by hand. So if you wanted to find your x-intercept algebraically, I'm just going to show it to you. You don't have to do it. You take your equation and set it equal to 0 and solve. Now, we solved these yesterday. What would you do first to solve this? How do we get rid of the 2? Divide the 2. Now, what's 0 divided by anything? 0. Next, we would do the wheel and write it as a log, right? Log base. Good. Anytime we take the log of a 0, it doesn't work. Your calculator's going to get an error message. You can't log negative numbers or 0. So that's why we get none. And if you tried to type it in your calculator, it won't work out. Now, y-intercept, we should be able to tell from our graph. So the y-intercept is y equals 2. Minimum So the minimum for this graph is where it levels off. So for exponential graphs, the minimum is where it levels off at. Where does it level off at? 0. Y equals 0. Does this graph have a maximum point where it stops? No, because the graph keeps going, so the max would be none. Now we need our end behavior. So what happens to the left side of the graph? Well, if you start in the middle and travel to the left goes up to infinity and beyond, like Buzz Lightyear. If we start in the middle and travel to the right, well, the right side of the graph, well, it goes to infinity horizontally, but end behavior is what happens to the y values as we go to the left. It levels off at y equals 0. Now, when you do intervals of increase, decrease, this is for what values of x does the graph increase? Well, this one is an exponential decay. So does it increase ever? No. So this is none. Since it's an exponential decay, it decreases everywhere. Now, this is where we have to write things a little bit differently. Some people are like, can't we use the little funny r for all real numbers? For this one, we can't because we want what is the interval that the graph decreases. So it decreases from negative infinity to positive infinity. You write it in this interval notation. It decreases everywhere from all negative numbers to all positive numbers. Now, domain is how far the graph goes left and right. This is all real numbers. We can put the funny looking r here because this doesn't include imaginary numbers, whereas your intervals of decrease, you can kind of think about it as including all of those values. So for domain and range, you can use the funny looking r, but that's only time. Now, range is how far the graph goes up and down. So notice it goes up forever, right? Does it go down forever? Does it hit all the y values? No, it starts at 0 and everything is graphed above that. So for your range, you say y is greater than 0. Can I put an equal to 0 on my range? No, because it doesn't touch this dotted line. It gets really close. So if you look for some similarities with things, in the range part and the end behavior and the minimum all have y equals 0, which is the HA, your ha. It's the ha. And then if you want to look at what parts of your graph kind of increase, decrease, this part would go with, does it decay or is it a growth or a decay? Okay, does that make sense? All right, let's try one more of these before we talk about a different type of graph, your log graphs. Bless you. So write down the equation and then just write the letters A through I because hopefully you already wrote them on the first problem. So it's the same A through I that we're finding. Bless you. Now, before you make the graph, pick out your three things, A, B, and HA. B is 2. What is A? 1. Because it's 1 times anything will make that number back. 0 would cancel all of it out. So A, if it's not there, is 1. -3 is your HA. Y equals -3. So when you make your graph, you start with HA and put a dotted line. So we're going to put a dotted line at -3. Then A is how far above that dotted line we make our y-intercept. So is our y-intercept up here at 1? It's here at -2 because it's 1 up from the dotted line. Now B is telling us that we have a growth. So we're going to start close to our dotted line, go through the y-intercept, and keep going. So does this graph touch the x-axis? Yes, it does, at some point there. Now, we can find our x-intercept by hand by taking our equation and setting it equal to 0. Well, no, because I just drew this line. Like, I could have drawn this part differently right here. I could have gone, right? I could have gone this way. I could have gone this way. I could have gone this way. So I don't really know where that value is. But we can find it by hand by doing this formula. We can set the whole equation equal to 0. Now, what would you do to solve this equation? Add 3 on both sides. Then we write it as a log. Write it as a log. Log base of equals x. So you do the wheel. Log base 2 of 3 equals x. So grab those calculators and type it in. What is log base 2 of 3? $1.58. So my x-intercept is 1.58. Now let's say that you forgot how to do that. You forgot what it meant to be a y-intercept, because to be a y-intercept, or the x-intercept, I'm sorry, the y value is 0. If you forgot, what else could you do? Graph it, right? You could graph it on your calculator. So I want to show you guys this and how to do this problem. So go to y equals, and let's graph this equation. Y equals 2 to the x. Don't forget to right arrow, and then you put your -3. I accidentally put a plus. So 2 to the x minus 3. Now go ahead and hit graph. We can tell from this graph it doesn't hit exactly at 2. It's somewhere in there. Second trace will help us find it. What's another word for y-intercept? 0. Oh, sorry. I accidentally turned that off. Yep. So second trace option 2, and your calculator will ask you some questions. Now here's where I like to type it in. It looks like it hits somewhere between what two numbers? 1 and 2. So you hit 1, enter, 2, enter. Your calculator says guess. You hit enter one more time. So 1, enter, 2, enter, enter. So we get 1.58. There's nothing else to intersect to. If you do intersection, you need a second equation. Now, you could put in the equation y equals 0, because y equals 0 is the x-axis, right? If you did that, then you could do intersection. Second trace 5, enter 3 times. That's a good shortcut to do, and that will give it to you as well. So if you put y equals 0 as the second equation, you can use intersection. I never even thought about that, so that was a great idea. But we got the same answer there. Now, the next thing we find is the y-intercept. Well, if we make our graph, we can find the y-intercept real quickly. It is at y equals -2. You can also find it on your calculator pretty easily. If you go to your table, when x is 0, you get your y-intercept. So the y-intercept is -2. Okay, does this graph have a minimum? That's where it levels off at. It levels off at y equals -3. Does it have a maximum? No. So say none. Now, end behavior, we look at the left part of the graph and the right side of the graph. So the left side levels off at y equals -3, but the right side goes up to infinity. So this gets switched from the last problem because the growth and decay switched. Does the graph increase or decrease? Increase because it's a growth. So decrease, you could say none, but it increases everywhere. So this is where you write in parentheses like a coordinate point, -infinity, comma, infinity. Domains all real numbers because the graph goes everywhere left and right. Is range all real numbers? Y is greater than -3. You're exactly right. So look for that HA. That's going to help you for anything that levels off. And look if it's growth or decay. That will help you with your end behavior, increase and decrease as well. Now the next slide I'm going to show you, you do not have to write down, okay? We're just going to look at it real quick and talk about it. Because the next thing that we want to graph and find key features of are log graphs. Now, logs and exponential functions are inverses of each other. That's what they're called. So here, when we look at this work that we used to solve for the x-intercept, it was an exponential function. We changed it to a log to solve. Now, when two equations are inverses of each other, their graphs are reflections of each other. So again, you don't have to write this down, but they reflect over the line y equals x. Now your calculator will make these graphs for you, right? So you don't actually have to graph them by hand, but we'll talk about some key things that happen. So notice how this exponential graph here to the left, y equals 2x, it starts off hugging the 0 and then goes up really quickly. If you reverse all of that, the graph on the blue, the log base 2 of x, hugs y equals 0, or not y equals 0, but x equals 0 now, because everything flips. So this hugs the line y equals 0. This hugs the line x equals 0. This is going to go down forever because this goes left forever. This goes up forever, so this is going to go up and right forever. See how they're just opposite directions of each other. And the same thing works with e to the x and natural log of x. Okay, so instead of leveling off horizontally, these level off vertically. But again, we're going to get our calculator to help us do this. So here's our next problem, log base 2 of x. You don't have to make a graph, and even on the homework that I give you, you don't have to make a graph of the exponential ones. That can be optional, making the graphs, because you can make your calculator make the graphs. You're welcome. And we can find everything that we need with the calculator and using our brains. All right, so first what we're going to do is graph this, log base 2 of x. So math option A, log base 2 of x. So remember, math option A. Also, you could talk about the translations for this. This doesn't move left, right, or up or down. It's a basic log equation. We hit graph, and it looks like this. Now, notice that on your calculator, it looks like the graph just stops. Do you think the graph actually just stops based on what we talked about? It just gets really close. Yep. So I'm going to sketch your graph over here on paper so that way we can see it. But it just gets really close to that x, or the y-axis, and it keeps going down. So this would be what it basically looks like. Now, the first thing that we want to find is our x-intercept. So going back to the graph, you can do it the way that we just did it, or kind of look at the graph. Where does it look like it crosses the x-axis at? At 1. Let's test it out. Hit trace 1 and enter. Well, x is 1, y is 0. Does that mean it's an x-intercept? Yes, it does. As long as the y value is 0, it works out. Now, if you wanted to do your second trace option 2, I would plug in 0, 2, enter on guess, and notice it still gives me the value. So type a number to the left, a number to the right, enter on guess. So x equals 1 is your x-intercept. Now, y-intercept. If you go back in your calculator, you can do the same thing. Under trace, you type in 0 for x. When x equals 0, it gives you the y-intercept. But do we get anything? No. That's because the graph gets close to the y-axis but doesn't touch or cross it. Just like the opposite, the exponential gets close to 0 but doesn't touch or cross it. So for this one, we would say none. Does this graph have a minimum? No, because it keeps going down forever, so that would be none. The maximum is also none, because as we keep going, notice how this is pointing. It's going to keep getting taller and taller as we go out. So for log graphs, both of these are none. Well, for left behavior, the graph points down, so it would be negative infinity. Well, if you start in the middle of the graph and go towards the left. Now, if you start in the middle of the graph and go towards the right, it keeps going up just really slowly. So the right side would be infinity. Now, looking at this graph, does it increase or decrease? It increases. It's this curve, and it's going to continually increase. So decrease would be none. But increase is a little bit different because we do increase for what x values does the graph increase. Well, do we actually have anything graphed over here on the left side? No. So it increases for any values of x that are greater than, what's this x value? 0. Domain is how the graph is graphed in left and right positions. Well, we don't have anything to the left before 0, so your domain is x is greater than 0. Think about it also as the equation. Can I plug in negative numbers here for x? No, we talked about that 2 days ago when we solved. You can't log negative numbers. Another way of figuring that out is looking at your table. From 0 and with the negative numbers, we get an error message, right? That's because it doesn't exist. Okay, range is how far the graph goes up and down. And that would be all real numbers. So if you compare this one to the first exponential one that we did, they're very similar to each other when you compare those two. Things are actually opposite of each other. So you have a lot of x equals 0 where we had y is equal to 0 or greater than 0. But it's still the same kind of concept. All right, let's do one last problem and then you guys will get homework and stuff. So here's our last one. Write this one down. We'll do a quick sketch of the graph. Now, before you graph this one on your calculator, too, think about how it translates, how it moves. So how is this moving? Down 2 and left 3. So left 3, down 2. So think about what that's going to do to the graph that we just graphed. Imagine it moving left 3 and down 2. But let's also type it in our calculator. was right. 3 plus 3 minus 2. 3 plus 3. Oh, why did that minus 2 go there? Oh. Minus 2. All right. So now that we hit graph, now our graph looks like it stops, but does it actually stop? No, it just goes down so fast that it doesn't actually draw it. So if I were to kind of graph it on my paper, it's starting down here. It's going to go up and somewhere over in that direction. That's just the basic format of what happens. Now, the graph that we did before hugged the, if we look at this one, it hugged the x-axis, x equals 0. What line does this graph hug? -3, because it moves left 3. So keep that in mind when you answer these questions. So the first thing we want to find is our x-intercept. I would just go back to the graph. Where does it look like it crosses at? Maybe 5? Okay, let's check it out and see. 5 or 6? So let's go second trace and option 2. Now, if we think maybe 5 or 6, go to a number to the left of that. So like 4. And then if you think maybe 5 or 6, pick just a bigger number, like 7. And then your calculator says guess, so you hit enter. So it crosses at 6. If you tried 4 and 6, it might give you an error message, so just make a bigger range. Okay? So x equals 6. Now, y-intercept, remember you can go back to your calculator and type in 0 for x, and the y value is -1. You could also look at your table when x is 0, y is -1. What do we put for min and max on this graph? None, because it doesn't have a true min, it doesn't have a true max, it keeps going forever. The left side of the graph goes to -infinity, and the right side of the graph goes up to +infinity. Now, this graph also increases like our last graph. But for what x values does it increase? The last one was x was greater than 0. This one's going to be x is greater than -3 because it moved left 3. And our decrease is going to be none because this graph goes up and over. So decrease would be none. Domain, very similar to intervals of increase. Where does the graph at? Well, from any numbers that are greater than -3. Range is how far the graph goes up and down. Well, this one goes everywhere. If you look at your end behavior, it goes down and up, so that would be all real numbers. Now, I know some of this is hard to think about, but I've given you 3 exponential and then 3 log ones to solve, and that's on the back of the worksheet. I didn't put any graphs on there because you don't have to graph. I just want to know the key features. So you can make your calculator graph these for you, okay? But if you want to graph them by hand, just use yourself some graph paper. And then the front is just describing your transformations like we did at the very beginning of class. Now, Monday is our review day, so we're going to review and do some practice problems and things like that. So this weekend, what should you do to prepare yourself for Monday? Sleep. Sleep is not the right answer. Good job, Peyton. We are going to review. So over the weekend, take just 15 minutes, at least 15 minutes. You can spare 15 minutes sometime during your weekend, right? Just say yes. And just go through and review your notes. We started with the exponent rules. We did exponent graphs. We did writing equations with 2 points. We did word problems. We did our log packet. We solved logs. We solved natural logs. And we solved exponential and then our graphs. When you get into Math 3, you really need to start reviewing and studying every day. to get ready for things. So take 15 minutes this weekend, study and review Monday, test Tuesday.